Okay, welcome everyone. I hope you can hear me. It's a great pleasure for me to introduce to you our speaker for today, Michele Pavanello, and his student, Pablo Ramos. They're both at Rutgers, Newark, but Michele and I knew each other from when we were still together at Leiden University, and then he started working developing in ADF, and then later on I moved to work for SCM in Amsterdam. And Michele then moved onwards to Rutgers, where he's now got his own group, and he's doing exciting things, not only within ADF but in other codes as well. But I'm looking very much forward to hearing him talk today about charge transfer using frozen density embedding. So I'll pass over to Michele now. If you have any questions during his presentation, you can try and type it in the chat box. There are some rest points along the way where he can look at that. And I see now that Michele's audio seems not to be working. So just type in the chat box. See if anybody else has an audio problem. So Michele is just logging out and logging in again, so it gives me a few more minutes to introduce his main research topic that he'll be discussing today, which is using frozen density embedding or subsystem DFT, which are a very neat way to describe processes such as Hall transfer or electron transfer within different subsystems. And so Michele is going to lay out the theory as to how that works, and then he'll describe some of the examples that he and his group have done recently, and he also will walk you through a hands-on example of how that works within ADF. And he'll also give you a bit of preview as to what will be happening in further development in frozen density embedding. Okay, so let me see if I can switch over to Michele now. He's still online. So let me chat a little bit more. So other groups that are involved in developing subsystem DFT are the group of Johannes Neugebauer at Münster University, Christoph Jakob, who recently moved to Braunschweig, and here in Amsterdam, where SCM still runs office space, we collaborate a lot with the theoretical chemistry group at the Vrije Universiteit. Luc Fischer is also actively developing subsystem DFT, and he's also working on wave function theory in density functional theory. A lot of exciting new developments going on in all of these groups, and again I'm excited to have Michele here today. So I'll switch over to Michele now, see if I can find him. And Michele says he will call it. Okay, Michele, I haven't unmuted you yet, so maybe that's the problem. Michele, okay. Okay, so sorry about the hiccup. I've asked Michele to become presenter, and in the meantime I'll unmute him. So hopefully, Michele, you can start talking now. Okay. Okay. Michele, I can see your screen, but I can't hear anything yet. Okay, Michele, I think now we can hear you.
Excellent.
Okay, so I'll shut myself up and hand over to you guys.
Okay, let me load up the presentation. All right. All right. So, well, let me say this. I do not see the chat, so I'm going to make frequent stops in the presentation so that you guys can have a chance to ask questions sooner than the end of the webinar. Okay. So here with me there is Pablo Ramos. Hi, nice to meet you. He's a co-author on several papers on this subject. Okay, so let's get started. Let me first tell you what my group is interested in so that you have an overview of who we are. We essentially work with subsystem DFT only. We really do not have other projects with the exception of very small other projects, so mostly subsystem DFT. With that, we look at charge transfer phenomena, electronic structure and couplings. We apply that to biosystems, organic electrode materials, and we wish to apply it to also to proteins, although we are having some difficulties because proteins are really large and complicated objects. All right, next we also ventured into looking at periodic systems, and for that we have our own subsystem DFT code, which was implemented in Quantum Espresso, and with that we can do both ground state calculations, single point, geometry optimization dynamics, as well as real-time TD-DFT and RMFS dynamics. However, RMFS dynamics has not been published yet, so I guess I should not advertise it to you at this moment. We've been applying this method to molecules at surfaces, but we're still really learning about it in these days. So before I can make that code available, it will be maybe another 6 months or a year. We also look into linear response to TD-DFT and van der Waals interactions, so this is less interesting to you guys. All right. So first, I'd like to make an overview of what it is that we are after when we calculate electronic couplings. We essentially want to calculate the coupling of sandwiching two basis functions, sandwiching the Hamiltonian operator. And we can do that in many ways. One way is by essentially first calculating the adiabatic states, which is that means essentially calculating the ground state and the excited states of your system, and then determining a sort of adiabatic to diabatic transformation. And this is done routinely by several people, and here I apologize if I am leaving out perhaps you or people you know. These are the people I know who have used this method more recently, and Marshall Newton, Robert Cave, Bob Cave, Alexander Wojciuk, Cherry Su, and Joe Subotnick, among many. Usually this method is associated with wave function method. So you have to take an accurate wave function method, you calculate ground and excited states, and then you use this adiabatic to diabatic transformation to then get these electronic couplings. This is very accurate if the method you use it with is accurate. So you can use TD-DFT as a method to calculate adiabatic states. But as we know, TD-DFT has encounters difficulties when looking at charge transfer states. So actually I do not recommend the use of TD-DFT for this type of calculation. However, you might find a solution that works for your case. This method usually is good for generating benchmark values and in most instances is this adiabatic to diabatic transformation is carried out with a Mulliken-Hash scheme. Then there are fragment orbitals methods. These are very fast methods because they assume a frozen core approximation. And this, again, is a number of people who have used this recently, and I'm sorry if, again, I'm leaving you outside of this probably. Ferdinand Grosema, Mark Ratner, Jean-Luc Preda, Jochen Blumberger, and Markus Elsner, among the many. This is really the most common method, and ADF has this under the transfer integrals keyword. This method, now, Markus Elsner and Jochen Blumberger have recently published a work looking at benchmark values, and this is the reference here, Jacob Feeds 140, 104, 105, 2004, and they've determined that their fragment orbital method as implemented in their code yielded about 20 to 40% accurate coupling values compared to the benchmark. And again, the benchmark was determined with this Mulliken-Hash diabatization scheme using wave function method. In this paper also they look into constrained DFT and how constrained DFT can generate diabatic states. And it shows that actually constrained DFT can do much better than fragment orbital methods. But here we are interested in frozen density embedding, and this method does not include or use the frozen core approximation. It's an all-electron method. It has been developed by myself and in collaboration with Johannes Neugebauer when I was in his group in Leiden, and also in collaboration with Lucas Bischer, and I guess here I'm leaving out another name, which is Troy Van Voris, who has helped us in the implementation of the coupling formula. This method you don't know yet, but we have submitted a publication showing that this method is better than 10% accurate on this benchmark set, essentially with almost all functionals that you can use. However, some functionals work better than others. Okay, so let me then transition to what frozen density embedding is and what are its strengths in theory and also in practice. And then after that, I will tell you about this electron transfer component of it. So essentially, frozen density embedding allows you to tackle large systems with, let's say, with a with an algorithm that is, in many respects, could be as accurate as the total DFT of the full system. Of course, there is one approximation which makes it less accurate in some cases, but in the cases that we are interested in, it is of comparable accuracy of regular DFT. Okay, so the idea is to split the system into several smaller interacting subsystems. So you can take the electron density of the total system, this rho of R, and write it as a sum of subsystem densities. Now this is an idea that is very old, well not very old, but dates back to probably mid-80s and early 90s. Let's see. Then you see that the energy functional cannot be additive, meaning you cannot write the total energy as a sum of subsystem energies, but what you really have to include is a essentially the interaction part of the energy functional, and that we call a non-additive energy functional. And that comes in three flavors: kinetic, non-additive kinetic energy, non-additive exchange correlation, and of course the non-additive Coulomb interaction. This is how we define the non-additive functionals, as you could have guessed. And you see that if you then use this if you use density functionals rather than orbital or other type of quantities here in these non-additive parts, you see that you can fold these non-additive components into a potential, which we call embedding potential. So the solution of the DFT equations look just like a solution for, say, an isolated rho 1 or an isolated fragment, but in addition to the isolated Kohn-Sham potential, there is also this additional embedding potential. So seems straightforward up to now. This is what the potentials look like. The isolated Kohn-Sham potential looks just like you would expect. Interaction to the nuclei, repulsion to the electron, and exchange correlation potential. And the embedding potential, again, does exactly what you would think. Attraction to the nuclei of the fragments surrounding you, repulsion of their electrons, and then potentials associated with the non-additive energy, exchange correlation, and kinetic energy components. Here, an S is missing here. So we have to make approximations for this non-additive kinetic energy, and the easiest approximation to make is doing LDA. However, we never use this LDA approximation, which here I'm showing you the analytical expression for this potential in the LDA approximation. However, we almost always use potentials that also depend on the gradient of rho. So we use GGA expressions. Okay, so before we go ahead, I'd like to open up the, let's see, I'd like to open up the floor for discussion. If you guys have any questions about the FTE method for determining electronic structures of large systems. So Fedor, if you can unmute whoever wants to ask questions, this would be a good time.
Well, I don't want to unmute everybody at the same time, as people, might be breathing. But if anybody has an urgent question, then you can type it in the chat box, and I can even open up your audio channel if you wanted to. So if there's any questions so far, just raise your hand. Just type I into the chat box, and I'll see if I can unmute you. Okay, well, I think you've been very clear so far, Michele, so let's carry this on to the next stage. I'll mute myself.
All right. Can you hear me, Fedor, now? Okay. Somehow now it's not working. Okay, now it's working. Okay, good. All right, so let's keep going. Now we have to apply this frozen density embedding method to a picture, a dynamical picture in which you have charge transferring from one subsystem to another. Whenever you have charge transfer, it's always convenient to work in a so-called diabatic basis. And here is the Hamiltonian operator written in a sort of like almost second quantized notation in a diabatic basis. So you have this diagonal energies for the initial state, and then this off-diagonal element for the communication between the initial and the final state. Now, how do we define these diabatic states? Well, that's essentially very subjective. It is now understood that you should localize charges onto a region of space that you can call the initial state of charge transfer. And then for the final state, then you generate a state which has charge localized on a region of space that you call final state. So we can achieve that in many, many ways, as we have seen in the first slide. One of them would be constrained DFT, in which you just simply constrain the charges on the initial state, on the region of the initial state, or on the region of the final state. But with so this here would be an initial state, a suitable initial state in which a donor is positively charged, and then this would be a suitable final state where the acceptor is positively charged. And so obviously then the coupling becomes a matrix element between a donor plus acceptor state, and then another state where the donor and the acceptor, now the acceptor is plus. So this would be the coupling between these two states. So you see, you have to carry out two separate calculations, one to generate the initial state wave function, one to generate the final state wave function, and then you can couple them. This is a depiction of what it looks like when you use a subsystem DFT. Essentially, the idea is that you first start a subsystem DFT calculation in which you put a positive charge onto one subsystem. This is for Hall transfer only in this moment. And then you determine the electronic structure of, say, state on the left. Then you switch the roles of subsystem 1 and 2. You place a positive charge on 2, and you make subsystem 1 neutral, and you generate another wave function, which then you place here on the right, and then you sandwich the Hamiltonian with it, and you get your the coupling that you're after. This operation of sandwiching the Hamiltonian is what was then implemented in the 2013 paper. Okay, so this is the detail, if you wish, of the coupling. We are after this sort of coupling here. You see capital phi I, Hamiltonian capital phi F. If you had Hartree-Fock, if you had the real molecular Hamiltonian and Hartree-Fock wave functions here, you would get to this exact relation in which the Hamiltonian coupling would then be the energy calculated with the transition density of in the initial and final state multiplied by the full overlap. So this is exact in Hartree-Fock and exact for the molecular Hamiltonian. However, here we're using DFT, and so we will have to make some approximations to make this work for DFT. Okay, what is this transition density? Well, if you have single scalar determinants, you sandwich the density operator, you get this expression where essentially you're sandwiching occupied orbital of the initial state, occupied orbital of the final state, sandwiched by the transition orbital overlap matrix. And that is a matrix in which the overlaps are determined between the occupied orbitals of the initial state and the occupied orbitals of the final state. You make this matrix, you invert it, you stick it here, you calculate this transition density, you evaluate the Hartree-Fock energy with it, and you get your coupling if you had Hartree-Fock. Now we have DFT, and specifically we have subsystem DFT. So instead of E here, instead of Hartree-Fock energy here, we place the DFT energy. So the coupling then becomes equal to the DFT energy evaluated with the transition density times the overlap. We're making an approximation here because the overlap is determined with the Kohn-Sham orbitals, and we know we shouldn't really do that. So this is an approximation. And by the way, this approximation is shared among essentially all diabatic methods from constrained DFT to transfer integral as well. Okay, so then if you use subsystem DFT, you gotta make this expression subsystem DFT kosher, and here you get, instead of the total energy evaluated on the transition density, we write it as a sum of subsystem energies evaluated with the subsystem transition densities, including this non-additive component. This is, in principle, linear scaling in the number of subsystems. However, it is as linear scaling as your method to calculate the Coulomb interaction. And by the way, I apologize here. The Coulomb interaction has disappeared in this formula. It should be here. Obviously, Coulomb is long-ranged, and it is inherently non-linear scaling, but it's a one-shot calculation, so we can say that even if it wasn't linear scaling, it's not a big deal. However, using linear scaling methods for the calculation of the Hartree potential, this can be also overcome. Okay. Does this method work? The simplest case would be just two subsystems. And this is an example from the original paper, together with Troy Van Boris, Lucas Vischer, and Johannes Neugebauer, 2013. We have looked at really only two systems in that paper, ethylene dimer and water dimer. Here, ethylene dimer is the interesting case because it's the case in which essentially if you don't get the coupling, the Hamiltonian coupling right, so to go back here, if you don't get this quantity right, you don't get anything right. You see here different monomer distances. We have calculated this overlap, and then the excitation energy, which in this case is just simply twice the coupling, because this system is completely symmetric. And you see that we compare quite well with Fock space couple cluster, which is a method that allows you to calculate charge transfer excitation energy in a size-consistent way, whereas equation of motion couple cluster methods are not size extensive, and so you see that they plateau off to a constant when they should plateau off to 0. Fock space couple cluster does plateau to 0, and we compare quite well with this fancy method. So we're quite happy. We were quite happy about this system. However, you can see here is a very small system, and we might be hitting a happy system for our method. So we clearly needed a benchmark for this, and that's where Pablo came in, and we have benchmarked the FDE-ET method, which is this method that I just talked to you about, against this brand new HAB11 set developed by, jointly developed by the Jochen Blumberger and Markus Elsner's group. We recently published. They used again Mulliken-Hush diabatization and fairly good wave function methods to determine the adiabatic energies and wave functions, and from that they determine the diabatic electronic couplings. Here I'm showing you how FDE-ET compares with the benchmark set when we employ the BLIP, PBE, and PW91 GGA functionals in the FDE calculation. You can see that it almost always goes well, with the exception of BLIP here for benzene. We have documented this problem for benzene in the paper, and as soon as it comes out, you'll see it. I have submitted it to the archive, but has not been released yet. I will. You can ask me in a few days, and I will, or maybe I can send Fedor a link once it gets released on the archive. You can see why BLIP fails here. We have an idea why that happened. This is completely changed in the case of hybrid functionals. They consistently show a good behavior. This is the case of benzene dimer. Of course, we've looked at 11 dimers, so we have quite a bit of statistics. We have also checked not just several exchange correlation functionals, but also non-additive functionals, both at the exchange correlation level and at the non-additive kinetic level, and also basis sets. So here you see is the mean relative unsigned error. So we're always below 10%, and that's quite good. For meta-hybrid and meta-GGA functions, we see a similar trend. However, you see that for larger distances, somehow these meta-GGAs and meta-hybrids are not performing as well. However, I mean, the performance is still quite good. Okay, so we have, to summarize this part of the webinar, I would say that we're fairly certain that FDE-ET works well for Hall transfer reactions. So the couplings you get with this method are good for Hall transfer. We are now in the process of looking at charge separation, meaning going from neutral to plus minus, and also electron transfer, so going essentially having an electron, an excess electron going from one subsystem to the other. Those cases are more complex because you may know that DFT in general has a hard time describing N-ions. N-ions are typically unbound in DFT. If you use a unbiased basis set, such as plane waves, then N-ions are almost always unbound. Of course, if you use a local orbital basis, they may be bound, but their orbital energies might be positive, and so that's an indication that although they look bound, they are unstable. So we are looking into that, and the way we are looking into it is by using self-interaction corrected functionals, as it was done before, and I'll show you a slide about it, also in collaboration with Johannes Neugebauer. And also we are looking at coupling FDE with constrained DFT so that we can constrain that additional excess electron to stay on one subsystem. That so far, initial tests seem to be quite good, so we're going to release that soon, as soon as we publish some papers on it. Okay, this is a fancy application of this method. Pablo was able to apply this method to a relatively large molecular system. This is a DNA pentamer. We are essentially looking at the whole transfer from one guanine to another guanine through a bridge of thymine in the presence of a counter strand, DNA counter strand. This was published last year in the Journal of Computational Theoretical Chemistry. Here is an example. If you do not include the bridge states, you achieve beta values that are this essentially how fast your excitation energies or your couplings are decaying with distance between donor and acceptor. Typically 3 beta equal to 3 is a typical typical beta for a charge transfer into the vacuum, through the vacuum. While if you have bridge states, then the vacuum level is much reduced and your tunneling wall is much reduced. Therefore, the decay constant becomes much smaller, and we saw that the decay constant becoming close to 1 if you include bridge states. In this case, the bridge states are thymine molecules. So Pablo Ramos had to calculate couplings between donor and bridge states, acceptor and bridge states, and bridge states, and then make a big Hamiltonian matrix, determine the Green's function for the bridge, and then compute the effective super exchange coupling between donor and acceptor. And that yielded a good number. Obviously, we didn't include dynamics, nuclear dynamics, so that's a big limitation. This code, as of now, is not fast enough to be able to include dynamics. However, you might want to, if dynamics is important to you, then you can simply benchmark transfer integrals against FDE ET, and if your couplings are good, then you can just simply use transfer integrals for, I'd say, determining couplings during a MD dynamics that would fold in dynamics in a rigorous way. Okay. So I promised you I was going to show you something about charge separation. Here, essentially, the initial and final states become different. You start with neutral initial state, initial subsystem states, and then instead charged final states in which you have a subsystem becoming positively charged and another subsystem becoming negatively charged. Another interesting way, a process to look at is by putting one subsystem into an excited state. This was done by Alisa in Johannes's group, using delta SCF for the FDE calculation of this subsystem, and then regular SCF for the acceptor subsystem, and then using this trick of running the FDE calculation with a different number of electrons for D and for A for generating the final states. And this actually yielded quite reliable couplings and excitation energies, provided that one uses a self-interaction corrected function. That can either be a hybrid functional, such as BH and H, or a model potential, such as the Seopt function. So if instead you use GGA functionals, you see these are the HOMO of the anion here on the left, and on the right here you have the HOMO of the cation. You see the HOMO of the anion, if you use GGA functionals, tends to become unphysical with unphysical shapes, and of course that also generates unphysical couplings. So how to predict that? Really, there is no way to predict it. You just got to run the test and make sure that your functional yields reasonable orbitals. But you would do that anyways, even if you do a TD-DFT calculation. This is a common practice, looking at your orbitals. Make sure that they are physical. Obviously, if you use a self-interaction corrected functional, you reduce the chances of your calculation going sour. And again, we are with Pablo, we are looking at ways to still use GGA functionals by applying a constraint on the anion so that the anion has physically shaped orbitals. But that is not yet available to the users, to the ADF users. All right, so once again, I'd like to open this for discussion. If you guys have questions, you can always use the chat. I'd be happy to answer questions now about this theory component of FDET and applications that so far we have carried out and that's been published. So if you have any questions, now is the time to ask.
Okay, yeah, so thank you, Michele, for the very clear theory so far. If anybody has any questions regarding this part, just raise your virtual hand in the chat bar, and you can either type in your question or I can unmute you if you prefer to ask it via audio. Well, I guess if not, then yeah, it would be good if we can see some walkthrough example. So I think you will show the water example, right, Michele? So we can still do some Q&A after your hands-on demonstration. So I'll hand back to you.
Okay, so let me show you some examples on the how to actually calculate these couplings with FDET. I will show you now some outputs so that you can see what the output looks like, and then I will fire up a bash shell and show you what also the input should look like. Okay, so the way you organize the workload for this kind of calculation is essentially dividing the calculations into 3 components. The first part is to generate the first diabatic state, which I'm going to call diabat A. And essentially you compute a state in which the donor, in this case for Hall transfer, the donor will be positive and the acceptor will be a neutral molecule. That will generate several tape files. We'll generate the tape file for the isolated donor and acceptor molecules, and we'll generate tape files for the embedded donor and embedded acceptor molecules for the diabat A as well as for the diabat B. Diabat B is a reverse case in which the donor now is neutral and the acceptor is being calculated with a positive charge. Now clearly you have to I suggest that you carry out these 2 calculations in 2 different folders so that you keep the tape files for this diabat A state separate from the tape files of the diabat B states. Then the electron transfer input file must be prepared manually. Now I shall say that to compute these diabatic states, you have to it is advisable to run what we call freeze and thaw calculation for the FDE component, and you will see it in a second what that is. But unfortunately, in ADF, freeze and thaw is not very user-friendly if you have unrestricted fragments, and in this case, D+ generally is a radical cation, and A+ also generally is a radical cation, so you have to run the freeze and thaw calculation manually, and I'll show you later what that entails. There is also some ferment in the Vischer group on making an additional module on PyADF, so that you can just simply use PyADF for running this type of calculations. And I know it's there, and I've actually used it, and it works quite nicely, but is not yet released. It might take a while, and this is Luc Vischer's domain, so he'll have to. You can inquire with him or with Fedor about this. Let's see. Okay, once you have completed these two separate FDE calculations for the two diabatic states, then you can run a third calculation with the electron transfer keyword that combines these two diabatic states to output the coupling. The input file for the electron transfer part of the calculation has two important keywords to include. One is the fragments keyword, and for that you need to use the isolated, you need to essentially couple the fragments that you are using with their isolated fragment tape file. And when I say isolated, I mean neutral and closed shell fragment tape file. So this T21 ISO RAW1 file and T21 ISO RAW2 file, these are closed shell neutral, so these are tape file of closed shell neutral fragments. Why you have to do this is purely technical. It was much easier for me to code this having already some quantities reordered in a fragment-like way, such as basis sets, I/O maps, and so forth. So fragments keyword can only take in closed shell tape-to-1 files, so these are the easiest files for you to fit with. Then the electron transfer block key, essentially there are several options for it, but really only you should consider only three options. The very first one is very important. You have to put it, is the number of fragments that you are considering in your calculation. And if you only have two fragments, which you almost always will, then you put number 2 here, numFrag2. But you might want to put more than 2 fragments. In the case of Pablo, how many fragments did you have, Pablo?
10 fragments.
So in his case, he had 10 fragments. You have to put 10 fragments here. The first 2 fragments are always the ones that interchange the charge for technical reasons again. And in that case, he placed a number 10 there. Then there are 2 options here, joint or disjoint. And I shall point out that on the ADF user manual, there is a mistype. Here it is said that you have coupled and uncoupled. That was the old nomenclature. Now it is joint and disjoint, simply to make things clear, to distinguish this method from the TDDFT FDE method, in which the coupled uncoupled nomenclature is used. So here instead we use joint and disjoint. For your purposes, for most people, I would say please only use joint. That really is the one option that we have fairly extensively benchmarked. This joint is still a sort of alpha version code. At this moment, actually, is even slower than the joint option. So it is there for purely academic purposes, and I would not use it. So use joint, and everything will be fine. Very important keyword is inv threshold. This inv THR, it is set by default to 10 to the minus 3. Now, if I go back here, and I'm sorry, I'm going to skip some slides. I go back here to this formula. You see that the transition density we use for the evaluation of the coupling includes an inverse of a matrix. Now, if that matrix is singular, you can see that the inverse is not defined. So obviously, the computer is infinitely stupid unless you tell it not to be stupid, and the computer doesn't know that a matrix may be singular, so it's going to try to invert any matrix you give to it. And of course, it's going to make a big mistake. You're going to run into huge numerical inaccuracies if you don't put a check on the invertibility of this transition overlap matrix. So the overlap matrix element will be always correctly determined, but this transition density might have some numerical inaccuracies due to this inversion. So what we do to fix that, and we learned this from Troy and Boris, what we do, we essentially we do a singular value decomposition of the overlap matrix, transition overlap matrix, and then the singular values that are below this inv thresh, or say the subspace related to the singular values below this threshold are not inverted. So for some system, so for most systems, 10 to the minus 3 works. However, you may see that in some cases 10 to the minus 3 does not work, and you have to use a higher threshold. So the higher you put this threshold, the more likely you are to invert that transition overlap matrix in an approximate way. So the higher this threshold, the more approximate your couplings are, but the more numerically safe they are. And in the JCTC paper with Pablo, we have extensively looked at this. Well, we have introduced this feature, and we have extensively determined its usefulness. Okay. Now, if you have a shell script, you can go to this path, ADF home examples, ADF electron transfer underscore FDE underscore H2O, and there is the example file for running this sort of calculations. What you should not forget to do, electron transfer doesn't say it explicitly, but it requires that on the folder where you run this electron transfer calculation, you have to have these fragment files, frag.a1.t21, frag.a2.t21. These are the fragment files. Specifically, this is fragment 1 and fragment 2 for diabat A, and this is fragment 1 and fragment 2 for diabat B. So you have to have these fragment files, tape files, in the folder where you run the electron transfer calculation. So if I go back one slide, here now you see that in output, in your workflow, when you compute the diabats, you just should save into frag A1 and frag A2 the T21 files for the embedded species. Okay. All right, so again, if you look at these example files, this is the output you should see. In the case of water dimer, because it's fully symmetric, meaning the water molecules are coplanar, then the LUMO of one molecule, or if you wish, actually, in this case, it's whole transfer. So if the HOMO of the acceptor is exactly orthogonal to the HOMO of the donor, so you have that you run into this issue of quasi-orthogonality, and the inverse of this transition overlap matrix becomes, the transition overlap matrix becomes singular. So this Penrose inversion kicks in, so this is what the warning says. Although everything is fine, if it kicks in, you're fine, it's numerically stable, you might want to check that also other configurations of your system are yielding correct couplings. You clearly see that the coupling is incorrect because you see that you get some unphysical electronic coupling when the inverse of the transition overlap matrix is wrongly carried out. In that case, you just increase the inv threshold to say 10 to the minus 2, and everything should be fine. Okay, so this is the summary of the output. You have the electronic coupling outputted in two units, electron volts, and wave numbers. H11 minus H22, this is simply the difference of the diagonal elements of the Hamiltonian, so this is the difference between the site energies. You have access to the site energies, full site energies here, H11, H22 here. However, this H12 also is printed here, but you have to be careful. This H12 is a non-normalized H12. You have to be careful on how you use it. So, in long story short, these raw Hamiltonian values, really you should only pay attention to the diagonal elements. The opposite is true for the overlaps. The overlap here, you see for the water dimer is 0 as you would expect, and you see here this raw overlap is 0. One thing that you see also is that the overlap of the initial state and final state, I mean the two diabatic states, are not 1. You would expect them to be 1, but they're not 1, and there is a very good reason for this, and I can talk to anyone who's interested in understanding this detail later. So let's look at a different output file. This is a different molecule which I took from Pablo's benchmark calculations. In this case, the site energies are almost degenerate, and therefore the electronic coupling is quite large. You see it's 0.34 electron volts is huge, and the excitation energy becomes twice that. It's 0.6. For this case, I forgot. I think it's a thiophene dimer, but I forgot exactly what dimer this is. And again, you see you have access to the raw diagonal energies and to the raw overlap. Now you see these overlaps are even smaller than 0.9. This is completely fine for the diagonal levels. And you see the off diagonal here is 0.058, but the one that is printed here in overlap is 0.06. Why this difference? Simply because we print the correct overlap that you should use is the normalized overlap, in which the overlap matrix will be normalized with this operation here on the bottom right of the screen. So you see that the excitation energies may vary from the diabatic energy difference. This is clear because if you have a symmetric dimer, obviously your diabatic energies would be degenerate, and then all the entirety of the excitation energy comes from the coupling. Okay, and this was true, by the way, also for the ethylene dimer case, which yielded very satisfactory results compared to couple cluster. Okay, so before we go to the summary, I'm going to fire up a shell. I'm going to show you, so I'm going to go to ADF. Let me first clear this from up there. ADF home, examples. So now I push tab, and you see that now the bash variable ADF home has been resolved into this. You might see a different value for your bash variable. Example ADF, and then electron transfer FTE H2O. You do ls minus L. You should see that you have two files starting with electron transfer. One is electron transfer underscore original.out.gz. You just simply do gu unzip that file, and what you'll get is this output file. And then this electron transfer underscore FTE underscore H2O dot run. So let's look into that file. I hope you guys can see this. I'm going to try to make my Zoom terminal. Preferences. I'm going to make my font. I'm going to increase my font so you guys can see it better. I'm going to make it bold. There you go. Okay, much better. Okay. So you see here in this example file, here there is the workflow I just mentioned to you. First, calculate the site energy using FDE, then calculate the charge transfer excitations and charge transfer integrals using FDET. Okay, forget about this error thing. I don't know why it's there. Okay, so the first calculation here is a typical ADF calculation of an isolated fragment, in this case water. You see atoms, water. I'm using the PW91 density functional, and I'm using the basis keyword here, numerical quality good. This pertains to the fitting and the grid, how fine the integration grid for the DFT integrations. I suggest you guys use this. However, it is not needed. You can also use a regular numerical quality, and your couplings will be good up to usually about 4 to 5 decimal digits in R3s, which means about maybe 0.1, 0.2, 0.01 EV. If you want any better than that, then of course you gotta crank up the numerical accuracy of the integrations. So you see this initial calculation ends here, and the tape file has been saved into this t21.iso.ro1. Then again, we do the same for the second water molecule. You see here, second water molecule. Here we impose, here we impose no symmetry. Again, the PW91 density functional. However, you are not required to use the same functional, but is if you have the fragments only of donor and acceptor, it is highly recommended you use the same density functional and the same basis. See again the basis keyword, the TZP and no core. And by the way, you cannot use core yet in these calculations. The first FDE calculation will make the donor plus and the acceptor neutral. So this is fragment 1, and it is positively charged. So you have to include both the charge keyword and the unrestricted keyword. Obviously, if you use a hybrid functional, you have to also include additional keywords related to running hybrids, such as you need to make sure that your fitting is, density fitting is of high quality, and you also have to make sure your basis set is free of linear dependencies by using the dependency keyword. Here we're not using hybrids, so we don't have that issue. You see the fragments key includes the isolated fragments in this first step, and the acceptor fragment is a spectator fragment and is a frozen fragment. This is the FDE keyword. We're using both the PW91K non-additive kinetic energy functional and PW91 exchange and PW91 correlation functional for the non-additive exchange and non-additive correlation. Again, you run then several freeze and thaw cycles in this configuration. This is just the second cycle for the now the acceptor to see a donor positively charged, and again now the donor has to be see the acceptor slightly polarized by the donor, and you see now that because the donor is a radical cation, we cannot use in this fragments key, we cannot use the embedded T21 file when it is when this fragment is active. We have to use the isolated and then run a restart on the embedded file. This works very well, and you can just use this as a template for your calculations, just changing this atomic coordinates, updating this fragment cards. So this keeps going this way also for diabatic B. You save your file accordingly. In this case, they're saved all in t21.m.raw something. And then you go all the way down and you start your electron transfer calculation. Now you see, for the electron transfer calculation, you have to move the embedded tape files into the appropriately named fragment files for the electron transfer code. They have to be named with this nomenclature. This is for diabat B, and if you go up here, we see the same for diabat A. Let's see, yeah, right here. After diabat, the FTE calculation of diabat A was completed, then we moved the fragment files into the appropriate file names for electron transfer. You don't have to, if your fragments are big, you don't have to run a move. You probably you can probably get away with linking, do a link onto this file that would involve no moving, but again, moving essentially implies no moving of actual disk memory. Another thing that you may not want to do is to copy these files, if files are big, so consider alternative strategies to copy. Okay, so let's go back to the electron transfer. Okay, here I make very clear that now the tape-to-1 file has to be renamed into frag A1, frag A2, and frag B1, frag B2, and so forth. I do not allow more than 999 fragments here, but I doubt you will ever use 999 fragments in your calculation. The largest we have run so far for this was 10, right? 10. Okay, so this is the electron transfer. This looks just like a regular ADF calculation. The fragments, you place the isolated fragment files, as I mentioned to you earlier. You have to include these cards pointing the appropriate coordinates to the fragment name. And this is the fragment name that appears here. It's the same one that you put on the card here. It has to be of the correct spin state. So if the total dimer is a radical cation, then the electron transfer calculation has to be run with that same spin state. So in this case, charge 1,1, meaning it's a cation, and there is one more occupied alpha orbital than beta. We do not allow any SCF iterations. However, unfortunately, ADF will run one and build the Fock matrix. That may be a bit time consuming, and I apologize for that. There is nothing we can do at this moment for that. And so for this water dimer, the default values for everything work just fine. So you put just electron transfer num-frag 2, and that runs the calculation and gives you out this output that we discussed before. Okay, so I might as well conclude and tell you that we so far have coded this FDET in my group. We are still coding and adding, making it better, making it faster, and trying to add functionalities to it. And Johannes Neugebauer group also is actively working on it, looking at including as many spin states as possible. There was the code that was presented in the 2014 paper with Alisa Solovieva and Johannes and myself. However, that code is not available yet to the users, but there is a good chance we might put it in the next ADF version. It is still an alpha code, so it's not been thoroughly tested yet. I know also Luc Vischer and his group are working on this electron transfer code. It is quite nice to see so many groups working on it, and hopefully we can make this code work better and in a way make it suitable for as many systems as possible. I know Luc Vischer is also looking at ways to automatize the input file generation with PyADF, and I have a beta version of actually an alpha version of that. It works quite nicely, so I'm hopeful that will go will become part of the next version of PyDF. So some recommendations for you to keep in mind, and by the way, I will give these slides to Fedor, so these slides will be available to you anytime you want to consult them from the SCM website, I'm assuming. So these recommendations say that you really should stick to the PW91K functional. We are implementing additional functionals such as the rev up back functional, which is good, if not better than PW91K. However, we have not benchmarked it for the FDEET code, so I cannot recommend it at this moment. PW91 works just as well. Again, there are no particular problems applying FDEET to cations. You might need to tweak a little bit with this INV threshold if a near orthogonality is suspected. However, application to anions is not recommended. However, it is possible with the current code. If you use self-interaction corrected functionals, such as the SEOP functional or hybrid functionals, then you should be okay. However, just make sure that you are not running this in a black box way and that you are always double checking your results for a physical outcome when you apply this to anions. Very soon, Pablo will output a set of benchmark tests on anions. Recently, Bloomberger Group has put out a benchmark set for anions, HAB11M and HAB8M. Sorry, thanks, Pablo. And so soon we'll know about how FDET performs against anions. Again, application to charge separation, it is possible, however, not with the current released code for some technical reasons, but perhaps in the next ADF release, Alisa and Johannes have coded this nice extension to several spin states, so that can be included in the next version of ADF, possibly. This is all up in the air at this moment. Okay, so I might tell you also that I'm looking for PhD and master students. If you're interested in any of these available projects you see here, let me know. Send me emails, or if you are a professor, if you have students looking for the next step in their career, and if you like my research, go ahead and refer them to me. I should thank the people who make this possible. Of course, the group members in my lab who actively work on ADF and FDEET, the Balina, Pablo especially, and Mark, and as well as the collaborators without whom this would not be possible. So Johannes Neugebauer, who now is at Münster, Luc Vischer, and Troy von Boris. Some funding, which should always thank funding agencies, including ADF, allowing us to work with this really wonderful code. And my presentation has concluded, so I'll bounce it back to Fedor, and if there are any questions, I'll be happy to take them.
Okay, so thank you very much, Michele, for a nice presentation. Yeah, as you already remarked a couple of times, yeah, one of the nicest next steps would be to make it more automated in the sense of freeze-thaw kind of cycles. So obviously it will never be black box, but as you mentioned, people are working on using a Python interface for setting up the calculations for you so that you don't have to manually go through the labor of setting up your script to run all the freeze and thaw cycles that you need. Okay, so let me just first ask if anybody has a question at the moment. So again, you can raise your hand in the chat box, and then you can ask your question there, or I can unmute you in case you wanted to ask via audio. So any questions at the moment?
You can ask wild questions.
Well, okay. Well, let me start off. So I've got one question. In the electron transfer example for water, there's a huge energy difference between the two diabatic states, and that probably has to do with their orientation of the two water molecules. Is that all?
Can you hear me, Fedor?
Yep, I can hear
Okay,
you.
definitely. So essentially, the idea is this. Let me go back to this example here. You see this ethylene dimer is perfectly stacked. So if you take an electron out of this molecule, the radical cation will have the spin density completely delocalized on both ethylene on the right and ethylene on the left. The way then we approach this problem is by constraining the charge only on the left or only on the right, and then computing this coupling. Clearly, when you constrain the charge only on the left, you generate a state that is completely symmetrical with respect to the state of constraining the charge on the right.
Yeah.
So they will have the same energy. So the site energy in this case will be degenerate, but the coupling will be the one responsible for for the fact that in going from the ground to the excited state of this radical cation, you essentially go from a wave function that is completely symmetric to a wave function that is completely anti-symmetric. And that is exactly what we, the excited state that you hit if you model this with this simple 2x2 Hamiltonian matrix. And so that 2x2 Hamiltonian is enough to predict a pretty good excitation energies, even compared with Fock space couple. I mean, compared with much better wave function methods. So the trick there is that FTE is an all-electron method, and so all the effect of the orbital relaxation due to the charge is taken into account. If you use transfer integral, you would probably get good numbers as well, but that difference between this and transfer integral would be then the coupling difference due to relaxation effects, which are completely included in FDE-ET, as well as in other methods such as constrained DFT. Constrained DFT would have this also automatically included, but they're obviously not included if you make a frozen, a type of frozen orbital approximation in which you only include homos of frontier orbitals of neutral isolated fragments, such as in the transfer integral.
Yeah. Understood. Okay, so then just one more question from me. Of course, we can still take questions from the audience. Of course, if you're interested in seeing what happens in a charge hopping event, in, let's say, an organic crystal in an amorphous system, then once you move the charge from system A to system B, or from monomer A to monomer B, you'll polarize your environment as well. But you already have the densities available, at least if the coordinations are available. So in that type of approach, you could include polarization of the environment with the subsystem approach. Would you still then use freeze-thaw cycles for the spectator molecule, so to say, because one can expect that the densities will be polarized as well?
Okay, this is a very good question. So I'm going to go back here to this picture of Pablo. So in this case, you have the donor fragment, and then several other fragments, and then even several other spectator fragments. So what is happening here is that if you want to do this in the most accurate fashion, then you would have to do freeze and thaw. When you put the charge on the donor, you would do freeze and thaw on all the fragments, all of them.
Yeah.
And that obviously makes the computation expensive. I mean, I tell you this would be essentially impossible with regular DFT, or close to impossible. So subsystem DFT already makes this possible. It takes a long time, but it gets there. You will get the energy and wave function, density actually, of the donor plus in the presence of all the others. And then you do this for all the other subsystems, and you calculate your Hamiltonian matrix, and that would be the most optimal way to carry out this calculation. Another way is what you suggest, is by including only, say, densities evaluated for isolated fragments. So you can put isolated fragments here, and then compute the electronic structure of the donor plus in the presence of those densities of isolated fragments in the environment. That is definitely possible, and the way you would achieve it is by, here is by essentially adding additional fragments to your fragments key, and then in the FDE calculation, just simply putting the isolated fragment tape files. And that would include those densities in a frozen way, so there would be frozen densities, and your system then would see them without having to then do freeze and thaw over them if you don't want to.
Right.
And then just simply add those, the very same T2-1 files, to your electron transfer. So in that case, frag A, frag A1, frag A2, frag A3, some of those frag AN tape to 1 files will be the isolated tape files of the environment fragments. That's completely doable with this at this moment.
Okay.
So yeah, we can do both. We can do fully relaxed environment as well as only partially relaxed fragment, in which some subsystems in the environment are kept frozen in their isolated fragment density.
Yeah. Understood. Okay, so any other questions from the audience? Well, I think not. So, Michele, thank you once again, and thank you everybody for listening in. I'll make the slides available. I'll also upload a recording somewhere, probably tomorrow. So in case you wanted to watch this back or send it to some friends, and I guess Michele will also be available for questions later on via email, right?
Absolutely, absolutely. Both myself and Pablo are available to anyone who would who has any questions about this method. I should say also that you can find our contacts on my personal webpage. Just Google me and you'll find
well, I'll post a link to your website anyway once I upload the slides and the video. So good. Okay, well, let's close this session for now. And yeah, once more, thank you, Michele, and thank you everybody for watching.